Okay, I'm going to talk about digital pre-distortion next. Okay, so let's see. I have an example to go over. Well, is anybody doing? I'm just curious. How many of you are interested in digital pre-distortion? Quite a few. Okay. All right. Let me show an example. This is a relatively simple example that I think, for those of you who don't know what digital pre-distortion is, I think this will help you to understand what it is and maybe useful for you. But it's a simple digital pre-distortion example. Okay, this is where I'm going. This is the end result that I want to get to. Let's see this one. Okay, this is the result of a DPD simulation. What this shows is I have an amplifier that I've simulated with two tones using envelope, and you get intermodulation distortion due to the two tones. The red is after correcting for the AM to AM and AM to PM distortion. So this is the output power versus available source power, average available source power. In red, that's after correction. In blue is before correction. And this is the gain versus available source power. The blue is before correction, and the red is after correction. It looks like this instead of a single line because this amplifier has memory. So there's a spread. It doesn't move on the same line. If there are no memory, then you'd have just a single straight line here. So what this is a way to find the first order correction, say the static AM to AM and AM to PM correction, apply it, and then just see how much of an improvement we get. So this is looking at the spectrum here, the blue, you can see that there are blue spectral lines there. The blue is the spectrum before applying the first order correction, and then the red is after applying the first order correction. So there is an improvement. There's still this kind of indicates what memory is left or what memory is present after first order correction. So the way this works is this simulation finds the gain and phase correction. Let's see, that's one way to do it. Yeah, okay, so this finds the gain and phase correction. And the way this works is it uses the optimizer. Well, we have this power amplifier here, and I have this component. It's a linear S2P, a two-port S parameter block, and I have to find a gain correction term and a phase correction term, such that the output gain and the phase shift through the amplifier remain constant as we increase the source power. So I need, the way this optimization works is it calculates the initial gain for a small signal, a relatively small signal. It calculates the initial gain and the initial phase shift through the amplifier. And then as we step the source power, we have a source power sweep. During the optimization, we figure out how we need to correct for the gain. I mean, the amplifier starts to compress, so we have to basically pre-distort it. We have to apply gain, an additional gain to the signal, as well as a phase shift, such that the gain and phase at the output remain constant. And that's done via optimization. So this is a simple first order pre-distortion. It's finding the coefficients, the gain and phase corrections in a first order way, so to speak. So it's not a sophisticated algorithm. It's simple, but I think it's still useful. But the results are this. This is the let's see. This is the gain correction versus available source power. That's the term that was found by the optimizer. So this is, we have to apply this linear gain correction. And initially, when the available source power is low, then we don't need much of a correction. But then as we start to get into compression, then, I mean, there's gain expansion, so we have to reduce the gain of the signal. And then we need to apply a lot of gain correction as it compresses. Then this is the phase correction. Then these down below are the resulting corrected output signal with the correction applied. And the scale is tiny on both of them, so that it's working as intended. So then this is the this is the resulting correction applied. I'm running a two-tone simulation, so I'm applying a two-tone signal using the envelope simulator, and this senses the input power and reads the correction data out of a file and applies the gain and the phase correction. This is just a simple variable gain amplifier, and this is a phase shifter model. So it corrects for the first order AM to AM and AM to PM of the amplifier. And then as you set the tone spacing wider, then memory effects are more likely to appear in this amplifier. It's more likely to show up. So you can see, after correcting for the first order AM to AM and AM to PM, kind of the static AM to AM and AM to PM, how much memory remains in the amplifier. Okay, so yes, this is not really ideally what you'd like to do is apply a more sophisticated pre-distortion algorithm. But I think this is still useful for comparing different amplifiers. If you had to compare two different amplifiers, you probably want, you'd like to have the raw memory as low as possible initially. And I think this enables you to compare different amplifiers and see what the memory is. for a given input signal. So the output looks like this. That's what I showed at the beginning. And the memory could be thought of as what is the difference between the third order terms and the fifth order terms. Ideally, these two terms would have, the third order intermod terms would be identical. That would indicate there's no memory. And then also just from the this is showing data versus time actually. So the larger the spread is, the more memory you have present. Okay. Any questions about this?
그 전통적인 DPD 방식은 아니고 이제 아날로그적으로 저희가 저 AMM, APM 특성을 좀 좋게 하기 위해서 그 스몰 시그널을 집어넣어가지고 나오는 결과를 확인을 한 다음에 게인하고 페이스 커렉션 값을 찾아서 앞쪽에 넣어가지고 저 리니어리티 구간을 좀 더 개선하는 방법에 대해서 지금 설명을 드렸는데요. 혹시 관련된 질문이 있으시면 해주시면 감사하겠습니다. Okay, no, so we can go.
All right. Okay, so let me move on to a new tool that we've recently introduced. This is, I'm going to show it in ADS 2023 because I haven't installed it with 2024 yet. But this tool is I'm applying, I have a Doherty PA, and I'm applying the DPD Explorer, which is a new add-on tool for running DPD simulations. And you have to, it's a separate installation to ADS, but basically you launch it from, well, okay, so if you have it, then it'll show up here under tools app, and after it's installed, you should see DPD Explorer as an add-on. So I got this from tools, app manager, and then DPD Explorer. So if you don't see this, then you don't have it. You have to get it and install it separately. It's an additional separate product from the standard ADS release. So from here, after it's been installed, you select Tools, DPD Explorer, and that brings up this user interface. This is new. To my knowledge, we have not had anything like this user interface in ADS before. This is like a new use model. The DPD Explorer is actually running System View behind the scenes, which is our system simulator. And you specify various things. So this is the power amplifier that we're going to apply digital pre-distortion to. And you have to specify what the modulation source is, whether you want crest factor reduction or not, the type of digital pre-distortion algorithm, what type of modulation analysis you want to apply. So you can either click on one of these and it'll bring up it'll move to the page in the graphical user interface to allow you to select the signal, for example. So if there are various signals available in LTE, WLAN, 5G, radio, and there's also IQ files. So there are sometimes the test signals are satisfactory. They're what people want to use, but sometimes not. You may have your own IQ data file that you want to use, and that's okay. This will read in an IQ data file and allow you to use it in DPD simulations. So that is an option. And then for the DPD and inverse model extraction, you can specify the type of model you want to apply. Dynamic gain, a memory polynomial, or direct DPD. I think there's a new one now in the newer release. For the power amplifier, you can. If you're using the dynamic gain model, then you have to have, or you get better results if you have the S parameter data for the amplifier as well. That's part of the model. And then for the power amplifier, you have to specify the input port and output port. So here's the input and the output. And you specify whether you want fast envelope or not. Then, you can obtain the PA's gain compression curve if you want to see that, so you can see where it's compressing and estimate what the average input power should be. And then for modulation analysis, you can calculate things like adjacent channel power and error vector magnitude. It's also possible to get power added efficiency from this simulation. You can run a single run, or you can run a sweep. You can sweep some parameter like the input power, or have a bias voltage, for example, that you want to sweep, or some other parameter in the design. So there's some flexibility. And then the results look like, let's see. Let's see what these look like here. This is for a single run. This is the error vector magnitude with DPD without and with it applied. This shows the ACLR improvement. This is the ACLR, the original signal, and then this is with the PA prior to applying DPD, and then after DPD is applied. There's about between a 7 and a 9 dB improvement in ACLR. And you can see the correction in gain. The gain has been flattened, and the AM to PM is somewhat flattened as well. So you can try different algorithms, but this allows you to take a power amplifier and see how well different DPD algorithms can be applied to it and what results you can get from it.
네, 앞 시간에는 아날로그적으로 저희가 투톤 시뮬레이션을 통해서 개인 컴프레션 포인트를 좀 더 좋게 AM, PM 특성을 좀 더 좋게 하기 위한 방법을 찾아봤다고 하면 지금 이 시간에는 이제 실질적으로 DPD 알고리즘을 적용을 해서 모듈레이티드 시그널 소스까지 이제 저희가 제공을 하고 거기에 따른 EVM이나 ACR이 얼마나 좋아지는지를 보여드리는 툴이 2023년도에 출시가 되는데 이 부분에 대해서 소개를 드리는 내용이었습니다.